In this section, we cover two important aspects of materials physics: scattering cross-section and the equipartition theorem, which we will use multiple times and you will see elsewhere in physics and engineering. In many fields of physics, we talk about scattering. For example, a traveling electron that encounters a vibrating atom and scatters off of it. The way to characterize scattering in general is usually with a scattering cross-section, described by the area that the moving particle sees. That would be the cross-sectional area of the obstacle that is perpendicular to the movement of the particle. We are interested in relating the scattering cross-section S to the average time between collisions, which we denote with the Greek letter tau. Tau is also related to the mean free path L, equal to the average speed, here u, times the average time between collisions. To derive this relation, consider an electron that moves with a speed u between two collisions. Now, for this electron to have first scattered off the first atom and then hit the second, it must have traveled in a cylinder of a length equal to the speed of the electron times the time it took to go from one scattering site to the other. In the volume of this cylinder, there is exactly one scattering site. This is because we can consider both atoms as being half in the cylinder and half out. So if the average electron has a mean free path of L, then it traveled through a volume equal to L times S, the scattering cross-sectional area. That volume can also be written as S times U times tau. The number of scattering sites per volume, n sub s, can now be derived from the mean free path of this average electron. It is simply 1 divided by S u times tau, because there is on average one scattering site in the volume defined by the mean free path and the scattering cross-section. Solving for tau, we get that the average time between collisions is 1 over the scattering cross-section, the speed of the particle that is being scattered, and the number density of scatterers. Now this makes sense because the scattering time should be small if the scatterers are very large, if the particles are going very fast, or if there are many scatterers defined by the number of scatterers per unit volume. The concept of a scattering cross-section is very general. You will see it used in other areas of physics with a very similar equation, where the scattering cross-section can characterize photon scattering, X-ray scattering, neutron scattering, and so on. Now we want to think more specifically about an electron scattering off a vibrating atom. We think of atoms as being held in place with a spring-like harmonic potential. We know that the amplitude of vibration should increase with temperature, because temperature is a measure of kinetic energy and the maximum amplitude depends on the kinetic energy. We know that the amplitude is related to the potential energy of the atom. The potential energy depends on the amplitude squared, like in a spring, and therefore proportional to the scattering cross-section. The equipartition theorem from thermodynamics tells us that the average potential energy of the system is proportional to kT. Thus, the scattering cross-section of a vibrating atom should be proportional to kT. This then gives us a scattering time inversely proportional to temperature. Using this very simple argument, we have shown that by increasing temperature, we make the atoms vibrate more such that they cover a larger area, scatter more electrons, and decrease the time between collisions. We can now explain the temperature-dependent resistivity of a typical metal. In a good metal like copper, the electrical resistivity at room temperature tends to increase linearly with temperature. This is because the time between collisions with the vibrating atoms decreases with temperature. Since the electrical resistivity is proportional to the inverse of the scattering time, it should be directly proportional to temperature. This is why the resistivity of a metal can be described as a straight line increasing with temperature, where the proportionality constant will be found experimentally.